So for the lab notebook, lab notebook is where you store your raw data, pretty much. And you can work up and do calculations, but the primary purpose of the lab notebook is to store your raw data. And so let's take a look at this. I'll post this on Canvas as well. So a lot of you have been putting your raw data onto the report sheets, and the report sheets are meant to be given to people, reviewers or whomever, but you shouldn't be recording your raw data onto the report sheets, because if you give those away, then you have no record of having done the experiment. So you should start to transition. If you're recording your data onto the report sheet, transition to recording your data into the lab notebook. And this is going to be your permanent record of the experiment. That being the case, we need to adhere to certain things for the notebook. And so make sure on your lab notebook you have your name, lab section. That's optional, but at least your name in your lab notebook, in case you forget it. And then reserve the first page. I'd say 2 to 4 pages, but that's probably too much. You only need 1 page. If you didn't reserve the first page for table of contents, that's okay. You can tape in a sheet in there on the inside cover. Use that for the table of contents. But we need a table of contents in there. That means you're going to have to number every page. Normally with the lab notebook, we only record our raw data on one side and then just do miscellaneous calculations on the other side of the page. So you'll have plenty of pages. And so you could use this for both Chem 1A and 1B. There's not that much data that we take. And so I would just do it on one side. And then you should record all your data directly into the notebook. And it should be in ink. The raw data should be in ink. Calculations and reports can be in pencil. So if you're turning in the report sheet, you can write it in pencil in case you make a mistake. You can erase it. But if you make a mistake recording your raw data, then we just draw a line or two through it and then write the corrected value. We need to make sure the correction, the mistake, is still legible. What we record there, the raw data are observations, and observations are not a list of instructions. Instructions are called procedure. Observations are what you actually did. And so observations are always written in past tense. Procedure is written like in present or future tense. But let's say you're making some cookies or something like that, and we have a recipe for that. The recipe would be the procedure, but how you actually made those, how many chocolate chips or whatever you put in there, that would be your observations. And so we make this distinction between that. And so it's important that observations are in past tense. In this way, any deviations from the cited procedure will be noted. It's hard to follow the procedure exactly. We often don't because it just takes too much time. And so we just do the best we can, and then we just write our observations there. And so, for example, the procedure might say obtain 20 milliliters of water, record the volume to the nearest 0.1, but do you really want to get it right on 20? If it says about, no, it's too much time to waste to get it right on 20. You get it close and then just measure it. Combine this with 3 grams of sodium chloride, weigh to the nearest 0.001. And so something like this might read in your observations 3.013 grams of sodium chloride, and sometimes they'll write the source. Sometimes it's a chemical company like Aldrich, etc., or just a stockroom bottle. It was combined with 20.5 milliliters BI water in a 100 milliliter beaker. You might write sentences out like this. I usually don't. I just do it by pictures. For me, it's easier just to draw pictures rather than write something out like this. It doesn't have to be complete sentences. You can just have phrases there. Blank pages, it's considered unprofessional to skip a page or a significant amount of space on a page. So try to avoid that, but sometimes you need some blank pages for some additional observations before before you move on to the next experiment. So sometimes we have it. Permanent ink, as I mentioned before. Pencil, the graphite becomes illegible. Corrections. For corrections, we don't use liquid paper. We don't use correction tape. You know, sometimes the liquid paper will flake off or the correction tape comes off. So normally we just make a single line through the error and then just write the correction next to it. You don't want to make the error totally illegible. A lot of people do this by completely blacking it out, but it's considered poor practice to do that. You want to see what the error was and the correction accompanying it is. Each page should include the date. Heading, yeah, yes or no, you know, but at least the date. Normally, we prepare the notebook before lab. We prepare the notebook before lab by outlining the procedure. And so this is what's typically done. Let's take a look at this. So normally we'll put the title. You could just write it verbatim, or you could just condense it, like titration. And then maybe an objective. You know, for part one, it was standardization of what? What did you do in part one of the titration? It is a very common lab procedure that's done. I'm sorry? The objective was oxalic acid dihydrate. And to do what with the oxalic acid dihydrate? Yeah, okay. So part one was to standardize an unknown. It was known. It just wasn't known to the accuracy and precision that we needed. You know, the sodium hydroxide was roughly 0.1 molar, roughly. But that needed to be to a much higher degree of accuracy and precision. You don't have to prepare this because we already did this lab. using oxalic acid dihydrate. What do we call the oxalic acid dihydrate? We call that a primary what? Standard. Does anybody recall what two things a primary standard must have? Your primary standards are typically solids, and what should these solids have as part of their properties? Nobody remembers? It should have high purity, and it should have a reliable weighing form. And so at that time I talked about these. I said the dihydrate was very stable. It's not going to lose water, it's not going to gain water, it's maxed out, so it's very stable. If you have, let's say, an anhydrous compound and you try to weigh that on a balance, it's going to be picking up water from the air, and the mass is just going to be continuously changing. So we need something that's very reliable as far as weighing form goes. And so therefore most primary standards are solids, because we can get those in good weighing form. This is from before. And then what I do is I'll outline the procedure here. And then what I do is I divide it. I divide the page, you know. This 2/3 of the page I use as for the procedure, and this 1/3 of the page I use for observation. And so you could do calculations in here. I would have done the pre-lab calc here, you know, for determining how much. You could do it, or you could do it on, I would do it on the opposite page. A calculation you could do in pencil. Calculations you can always repeat as long as you have the data. And so for the data, the raw data itself has got to be in ink. Procedure doesn't need to be in ink, but the observations do need to be in ink. So the procedure you can write in pencil, usually. Or you may or may not, depending on your observations over here, you know. So I would do something like 8.3 milliliters of 6 molar NaOH, this, plus, you know, about to get a volume of about 500 milliliters. On your observation, you'd write how many milliliters of sodium hydroxide you got. You know, this doesn't have to be so precise, but let's say you got 8.35 milliliters sodium hydroxide. And then you just show, okay, you know, we diluted it to about here. This is about 500 milliliters. So the observations can be very quick. If you prepare your procedure in lab, the observations are usually quick, just numbers and little things here and there, you know. So a lot of people do this, especially if you're finding yourself running out of time. If you find yourself running out of time in lab, this is the way to do it. This is the way to get very fast in lab. You know, you can get in there and get out very quickly. So a lot of people do this. Even if it's not required, they do this. And then we just finish. And so we just got to collect certain data. I mean, this would be raw data. This would be in ink here. This would be raw data. Things like this, for raw data, we don't usually put washing unless it's washing a precipitate, stuff like that. Normally, if you go to, or if you're working in a laboratory, you have to verify. I mean, sometimes this lab notebook is a legal document, so you have to get it signed. I say get it. Notebooks must be signed by the instructor before you leave the lab every day. I haven't done that yet, but this is normal procedure. This signature page where you sign it and the instructor or witness signs it. But if you prepare your notebook before lab, it just makes the lab go a lot smoother. Data tables should be entered into the laboratory into the laboratory notebook prior to lab. Useful information, such as important equations, mathematical, chemical, like calculations, should be recorded there, so you have it in one source. It's much faster to read or go through your notebook than the lab manual, usually. And so this is why I did this. I did this for every lab class I had. Some instructors will make you write the procedure verbatim. I didn't like that, though. I had some instructors make us write the procedure out, and I thought it was a waste of time because it's already written in the lab notebook, lab manual. And so I'd much rather sketch it out or outline it. All right, now once we collected our data, then we do our calculations and do our data analysis in the lab notebook usually. But we're not quite done with it because we have to do the laboratory report. The laboratory report, most of the labs we do, we just fill out the blanks, fill in the blanks. And so you have the report sheet at the end. Report sheets are meant to be clean and neat, because you're trying to make an impression on people. The lab notebook can be a mess. If you look at most people's lab notebooks, they spill all kinds of chemicals on there, and they look like a total mess. They make mistakes, calculations, stuff. But you don't want your lab report to look like a total mess, with chemicals spilled on there and all kinds of mistakes with calculations and stuff. And because that's what's going to be graded usually, is your lab report, not your lab notebook. And so lab notebook is, this is where you make the mistakes, and then you can prepare a nice and neat report sheet. I've had lots of instructors who graded on neatness on the report sheets. Again, report sheets can be done in pencil. But after obtaining experimental data in the lab notebook, you need to figure out what it all means. So in other words, you need to analyze and interpret the observations and draw conclusions based on this data. Once this is done, so first off, the first step is, do you know the percent sulfate in your sample? Did you guys get it? Well, the first thing is you better calculate the percent sulfate. And you did 3 trials, right? And those 3 trials have the same unknown, so those 3 trials should have the same percent sulfate. And so, first off, tell me how much sulfate you had in your unknown. And that was the goal of this experiment. So, okay, so we've done that. We figured out how much percent sulfate we have. Okay, once this is done, you'll write a lab report summarizing the experiment. The purpose of the lab report is to efficiently communicate the net results and conclusion of the experiment. This can be done in many ways. Okay, you're going to see a report sheet for 1B, but we're not going to do that for this one. In Chem 1A, the report format is found in the report form contained within the lab manual. Although you'll be filling in the blanks, you should note that the report will often require transcription of key data from your notebook, followed by a report of pertinent observations and calculations, finally an interpretation of the experimental results. Okay, that's not what we're going to do for 1B. When preparing your reports, please do calculations and answer the end of the lab questions in the notebook first for your own record, since reports are typically meant to be given away and not returned. Yeah, reports are meant to be given away. That's why you make multiple copies and you give them to various people. A typical report. Afterwards, copy one representative calculation using the data set and the answers to any end of lab questions neatly into the report sheet. Neatness and organization of the report count. Unlike the notebook, you may use pencil for the report. Please staple. Oh, that's lab reports, unless announced or otherwise due. Okay, what we're going to do for I might as well finish this here. I'll post this on Canvas. We're just transitioning over to the standard way of doing lab, which is this. But a lot of these safety rules are just common sense. But there are some written safety rules we'll look at. A good laboratory technique. These are things. The laboratory technique grade, let's say for example at UCSB, this is where I got this. This is worth like 20% of your grade there. And so efficiency with accuracy. You know, how efficient are you in lab? We had to grade people on that. That's part of the grade at UCSB Chem 1A. Safety, neatness in lab, including post-lab cleanup, lack of excessive breakage, and actual technique. And so altogether, these things were combined into 20% of your laboratory grade. For me, I don't. Most of your grade is going to be based on your reports. Here, primarily. A little bit on the notebook and a little bit on lab technique. Okay. We'll post this. All right, let's take a look at the report itself and see what we need to do about the laboratory report. But I seem to be missing my laboratory report document here. I'm sorry? Next week. All right, sorry, give me a moment to grab the report. Resume here. ACS stands for the American Chemical Society, and this is their style guide. American Chemical Society publishes a lot of journals. The most important one is the Journal of the American Chemical Society, JACS, but they have a whole bunch of others. And so they're one of the major publishers. For other journals, they have slightly different formatting requirements. But this is for ACS publications here. But even cross publications under the ACS umbrella have different style guides. So they're individual style guides for individual publications. And they have all of them have a different look, different organization, slightly different organization. So for example, Nature magazine, which is not published by ACS, is a totally different format. ACS. I'll post this on Canvas too. But the first part is who's your target audience? And so who is the audience? The other stuff is what journal to publish in. But the audience is going to be somebody who has about the same level of chemistry as you do, so you don't have to go back and explain everything. They should know what's going on. And so that means you will, what will you need to tell them that they don't already know? Well, they should have the same background as you, so you don't have to tell them much. But you do have to tell them some things, and so we are going to talk about what types of things you need to tell them. For example, you know, what was the purpose of the hydrochloric acid? What if you didn't add the hydrochloric acid? Would you still be okay? And so you would need to tell them that, because even though they might have a Chem 1A background, they might not know why you added the hydrochloric acid. You know, because we added the barium chloride. The barium chloride will precipitate out with the sulfate to make barium sulfate, but why would you add hydrochloric acid? So we have the unknown, which contains sulfate, plus barium. Barium and sulfate come together to precipitate. Why do we add in a third reagent, hydrochloric acid, to that? So it's sulfate, barium chloride plus hydrochloric acid. Why the third reagent? Does anybody remember? Nobody remembers?
I don't even remember adding hydrochloric acid.
You don't even remember adding hydrochloric acid? Well, you got to explain that type of stuff, you know. So even though they have the same background as you, they probably don't know why bother adding hydrochloric acid. It's just a simple metathesis reaction, isn't it? Probably like sodium sulfate plus barium chloride yields barium sulfate and sodium chloride. Should be simple. Why did you heat it? So these types of things, even though, again, maybe they know, maybe they don't, but we got to assume they don't know. You know, why did you heat it? Usually when you want to maximize precipitation, you cool it in an ice bath. Because when you cool things in an ice bath, you know what happens to the solubility? Usually, like, can you dissolve more sugar cubes in hot water or ice water? Or does it make a difference? Yeah, if you heat it up, you can dissolve more sugar cubes. So why are we heating it up when we're trying to precipitate it? Doesn't make sense maybe to a normal Chem 1A student. So we got to talk, why did we heat it? So these types of things are going to be all explained in the report. It'll clear everything up. And so this is what you're going to do for it. So just simple things. Of course, we want to avoid slang, but we got to use jargon. I mean, we got to use chemistry jargon. You know, it was funny. It was I remember one of my coworkers was writing a report, and she was telling me, she couldn't think of the word, so she just put in the thing, the thing that you're going to mix it with that. And so it was kind of funny. She was joking, but yeah, we got to use some jargon there, the chemistry jargon. And anyway, this is just certain stylistic things here. So you can read through this. I'll put this up today. Let's go to the format. The first thing we have is the byline. The byline is like the title and the authors and their affiliation. And there are different ways we can do the byline. So whatever byline you use, be consistent. Papers by J. Smith, J.R. Smith, John R. Smith, Jr., etc. will not be indexed in the same place. This is for searches. There are two things that get searched in search engines. One is the byline and the title, the other is the abstract. So you have to have certain keywords, and when you publish in journals, they have like certain lists of keywords that you should use to help the search engine out. And then affiliation would be like El Camino College or something of that sort. You know, they'll write their university or business or whatever. Do not include professional or official titles or academic degrees. The first or the last author is generally considered the senior author. So a lot of people want to be the first author or the last author on papers because those are the two most important. Usually it's the first author that does all the work. So when you read a paper and there are a whole bunch of people on the paper, authors, it's the first person who did the bulk of the work. And usually that bulk of the work is like 90% of the work or more, or 100%. Not always, but you know, that's what people assume. Also, we indicate the author to whom correspondence should be addressed. Usually the correspondence is addressed to the last author because the last author, they're permanently there, whereas the first author is probably going to move on. The affiliation should be the institution where the work was conducted. If the present address differs, then you usually give it a footnote. Okay, so the byline is pretty simple, just the title. You know, what would our title be? Just think of a simple title. What was the title in the lab? Gravimetric determination of sulfate? Yeah. We could do something like that. Maybe gravimetric determination of the sulfate in an unknown white solid. You know, something like that. Maybe a few extra keywords. It's not like a black tar or a liquid. You know, so we should have some more descriptive terms in there. Pretty much all journals. It says many publications, but it's pretty much all journals require an informative abstract accompany every paper. The reason is what the abstract is it condenses your paper into one paragraph. And in the abstract, you should be able to find all the key findings. The abstract shouldn't force you to read the paper. People have very little time because there's, maybe 1 million pages of scientific research published every year. You know, it's hard to keep up. You know, it just keeps growing and growing. And so your target audience, I'd say, let's say 100 people read your paper. Well, out of that 100, probably 97 will read only the abstract. And from the abstract, they get everything. They know. If I read the abstract of your paper, I should know how much sulfate you found in there. You shouldn't keep it like a mystery, you know. You shouldn't say, okay, read the rest of the paper, and then I'll tell you at the end. You know, people will get pretty pissed off if they have to read the entire paper to find out how much sulfate you had in your unknown sample. They want to know right away. So it's a spoiler for the paper. But they might want some details, you know, might want some additional details, and then they'll read the whole paper, you know, if they're really interested in seeing how you did it. So I'll just read this here where you can follow along. So we need an informative abstract. For a research paper, the abstract should summarize the principal findings. And so we need to know how much percent sulfate you had. Okay, we're not writing a review paper. What a review paper does is it looks at all the literature involving a certain topic, let's say a COVID-19, and then reviews all that, you know, into a certain aspect of that. And so those are review papers. Review papers are very good. And if you're learning a new subject, you know, when I started off researching a new area, you know, I tried to find all the review papers because the review papers save you a lot of time. rather than going back to all the original papers. The abstract should describe the topic, the scope, the sources reviewed, and the conclusions. You should write the abstract last to be sure that it reflects accurately the content of the paper. Yeah, sometimes I wrote the abstract first, and sometimes I write it last. Sometimes I write it first just to have a general outline of the paper. And so I'll just do the abstract as an outline of what I'm going to write for the entire paper. The purposes of the abstract are to allow the reader to determine the nature and scope of the information given in the paper and to allow editors to pinpoint key features for use in indexing and eventual retrieval. So just the first part we're interested in. The nature and scope of the information. The abstract must contain sufficient information to allow the reader to decide whether to read the whole paper. That determination comes when, if there's something they have a question about. They'll read the entire paper or parts of the entire paper. The abstract should provide adequate data for generating index entries. This is all for search engines. Although the abstract should not be a substitute for the article itself, it must be complete enough to appear separately in abstract publications. Often authors' abstracts are used directly in chemical abstracts. Chemical abstracts just publishes only abstracts. So it used to be a print publication. You get a print publication and all you find are abstracts. And so abstract needs to stand alone because oftentimes they'll just cut it out. When you do a search, especially for a lot of publications now, they require a payment for the paper. It usually costs like $30 or $35 if you want to do it that way. I mean, they're free, but free sources, but those are getting around the copyright. So usually you could read the abstract for free, but if you need the entire paper, you got to pay extra. Libraries already pay this. The amount of money they spend on publications is huge. In the abstract, okay, let me make this text a little bit bigger. In their abstract, you should briefly state the problem or the purpose of the research. So what was the problem or the purpose of the research we did? What were we trying to do in this lab? Find how much sulfate is in some white powder, right? Why would you want to know how much sulfate is in white powder? Why you would want to know how much sulfate is in white powder is what you put in the introduction section. And the introduction section is, why are you doing this research? What is the significance of this research? But usually in the abstract, we don't put in why we're doing it. We're just putting in what we did. When that information is not adequately contained in the title, maybe it is adequately contained in the title, because what was our title again?
It was just like
Gravimetric determination of sulfate in an unknown solid. So we don't want to be too repetitive. In fact, we don't want to be repetitive at all. The word limits, it's hard to get under the word limit sometimes, because they restrict how many words you can publish in your paper, and that means they want like really concise language. They don't want too much repetition. In fact, they don't want any repetition. And so sometimes you just have to keep cutting, and it gets harder and harder. indicate the theoretical or experimental plan used. So we didn't have a theoretical plan. We had some, well, I guess it's, in a way it's theoretical, you know. Why did we add the hydrochloric acid? That kind of stuff. Accurately summarize the principal findings and point out major conclusions. Includes chemical safety information when applicable. Chemical safety is if there's something hazardous about this particular experiment, you know, that you want to warn others about, then we'd include it here. We didn't have too much. You know, barium chloride's a health hazard a little bit. And then sulfuric acid, hydrochloric acid, but those are common chemicals, so. Do not add to, evaluate, or comment on conclusions in the text. You know, we don't add to anything. The abstract is just a condensed synopsis of the paper. And so there's nothing extra here. The abstract should be concise and self-contained. It's self-contained because sometimes that's all that's published, and that's all that 95% of the readers or 97% of the readers read anyway. Should be self-contained. The optimum length could be 2 sentences. It could be many more, depending on the subject matter and the length of the paper. Ours, it might be hard to get it in 2 sentences. Could you get it in 2 sentences? It might be a little difficult, but sometimes they'll force you to put it in 2 sentences, and then you'll have to figure out how you're going to cram everything in there. I think a short paragraph is what ours is going to be. Use meaningful nomenclature, that is, use standard systematic nomenclature where specificity and complexity require, or use trivial nomenclature where it will adequately and unambiguously define a well-established compound. We have no citations in the abstract. Do not cite references, tables, figures, or sections of the paper. So in abstract, it's very frustrating. You know, it says refer to table 2, but there's no table 2 in the abstract. You have to pay another $35 to buy the paper. We don't want to pay $35 to buy the paper. Just give us the data. And so you never reference anything in the paper. The abstract, this is just repeating that the abstract needs to stand alone. You may refer to equations or structures presented in the body of the paper if they are on a single line and can readily be incorporated into the abstract. So what you can do is you can incorporate an equation from the abstract, incorporate an equation from the paper and put it into the abstract. But single line means that they don't want to waste any space. This is especially the case if the abstract is used in the secondary literature. That is, it's only published as an abstract standalone. Do not include equations and structures that take up more than one line. Use abbreviations and acronyms sparingly and only when necessary to prevent awkward construction or needless repetition. Define abbreviations at first use in the abstract and again at the first use in the text. And so we have to do this because both sections is standalone. So the abstract is one paragraph synopsis of the paper. And then now we're into the main body of the paper. The main body of the paper, we have an introduction section. And so you can do the abstract at the end, or you could do it at the beginning to try to kind of focus you. Either way, I've done it both ways, at the beginning and at the end. I mean, if I already have a clear outline of the paper in my head, then I'll do it at the end. You know, if I'm kind of uncertain how I'm going to write the paper, then I'll do it at the beginning. So the introduction is to give you some kind of background information. It gives you the introduction is kind of flexible. It could give you background information on for example, sulfates. You know, what's the big deal? Who cares about how much sulfate is in there, right? What is the importance of sulfate? So the background might try to tell you why they're doing this. I mean, why should anybody care about sulfate? You know, that could be one. Or the background information might be like gravimetric analysis. You know, talking about, okay, the technique of gravimetric analysis. You know, how long has gravimetric analysis been around? Some people have written about this. You know, it's been around for a long time. Gravimetric analysis was used probably in the alchemy days or before. Or a combination of those things, you know. It could be done. You know, there are lots of things that could be introduced here. For example, remember where I was talking about the unknown, getting the unknown to dissolve to free up the sulfate? You guys remember that? No. You were lucky because the sulfates were the sulfate unknowns were pretty soluble. But what happens if there was an insoluble unknown? What would you have done? That's more difficult sometimes. So, you know, that could be in the introduction section as well, just some background. So a good introduction is a clear statement of the problem or project and why you're studying it. This information should be contained in the first few sentences. On the basis of your answer to the question of what the readers already know, give a concise background of the problem and the significance, scope, and limits of your work. Outline what has been done before by citing truly pertinent literature. So some people did look up things like, you know, sulfate analysis in the literature, gravimetric sulfate analysis. Has it changed? You know, since the 1800s or something, 1900s, pretty much the same. And then reference it, you know, if you find a paper. Here, there are different ways we do references. We could do either endnotes or footnotes. I don't care which one you do, endnotes or footnotes. Doesn't matter. But do not include a general survey of semi-relevant literature. So, you know, just the pertinent literature. State how your work differs from work previously published. Or state how it is related to work that has been previously published. So we need to give people a background, you know, the current state. You know, this is like a mini review paper because what you do, especially if it's a problem, let's say there's a significant problem that people are looking at, and in the introduction, they'll give a review of what has been done in the past. Yeah.
We need certain background of like other people.
Yeah, but you know, obviously you don't have access to the because our library only has a subscription to certain journals, and so our library you can't really do a complete literature search. You'd have to go to a full research library to get a full, complete literature search of everything that's been done. And everything that's been done, some of it's not so relevant. But you can find stuff on just like, what's that, Google? Have you searched Google Scholar before? Yeah, Google Scholar has quite a few papers, but it's still not complete. If you need to do complete, you'd either go to maybe Dominguez, which is the closest, or UCLA or Long Beach. You know, there they pay a lot of money for subscriptions to these search databases, and then you can get complete things. A lot of things I had to, when I was at UCLA and UCSB, you know, they have a nice interlibrary system. So if UCLA didn't have the journal, they could get it from somewhere else. So I got journals from like East Coast libraries there. Like one journal I got from, they just made a copy of it and sent it to me. was a paper and an old, it's like from the 1800s. And they had it, I think it was at Yale or someplace like that. And so they have these agreements you can do. But whatever, Wikipedia has information about gravimetric sulfate determination. I mean, that works too.
Are you gonna want us to find outside sources for hours?
What's that?
Are you gonna want us to find outside sources for hours?
You can if you want. I'll tell you, people have. People have found all kinds of stuff. But it's up to you, you know. They found it without going to UCLA, and they found it without going to, they just did an internet search, like Google Scholar or other things. You can find a lot of information out there. So this is outlining what has been done before. You need to do a literature search. It's not easy without that, but you can outline what some stuff has been done before. Demonstrate the continuity. So how does your paper fit into all the grand scheme of whatever you think? You know? Your introduction should be at least 1 or 2 paragraphs long. Ordinarily, the heading introduction is not used because it is superfluous. Opening paragraphs are always introductory in nature, or usually introductory in nature. So we don't have to have the heading, but I don't care. If you put the heading in there, it's fine. A lot of people say it's wasted space, you know, and that wasted space, when you multiply it by how many thousands of pages they do, that's like how many trees did they have to cut down just to put in introduction in there, you know, or how much cost is it? Although journals nowadays are all online, so fortunately they don't have to cut down so many trees as they did in the past.
And we don't need an introduction, or?
No, they're saying the heading. Most people don't put a heading here, introduction, because the first paragraph is always the introduction, is what they're saying. But it depends on the journal, because each journal will have different standards. Let's we can get some journal articles. This is, well, ResearchGate's probably free. New Journal of Chemistry. I haven't even heard of this one. See, in the New Journal of Chemistry, it's part of their style guide to write introduction here. This is all that's saying. Whereas in this Journal of Organic Chemistry, Bilstein, whatever, please pronounce that, they don't, you see there's no introduction here, so the first paragraph is always an introduction. This is a review paper here. The review paper, the creative science of organic chemistry is one of the few which has the power constantly to rejuvenate itself, because almost uniquely it studies what it also creates. So this is a review article, editorial. Oh, this is an editorial. Maybe it's not a good one to show. Whereas let's take a look at this one. So here is the title, Supramolecular Architecture and Photophysical and Biological Properties of Ruthenium-2 Polypyridyl Complexes. And so these complexes we study in Chem 1B. And so this is the byline. These are the authors. What's missing is their affiliation. Usually they'll have an affiliation here. I don't know why. It must be because they have multiple affiliations. A, B, C, D are their affiliations. So if we go down here and look at A, yeah, they're all at different universities here. This is Howard University, Washington, D.C., and then the other ones are in India here. And so we read the abstract. The abstract should give us a one-paragraph synopsis of the whole thing, and including their final conclusions. Let's see if it's at the end here. The cytotoxicity of complexes against a cancer cell line has been studied by MTT assay, and cellular localization of complexes within the cells has been monitored by fluorescence microscopy. 1 through 3 exhibit potent anti-proliferative activities against a panel of human cancer cell lines. So here we get the ultimate conclusion. 1 through 3, this is 1, 2, and 3, have been effective at anti-proliferative activities against cancer cells. So we know what they did. And we know now if we're interested, how effective, usually we want to know how effective is it? 100% effective, 90% effective, 50, 40% effective? That should be in here too. In the abstract, we don't want to have to read the paper, When they say how effective, we need it more quantitative. And so if they have some kind of percentage, maybe they don't have any percentage here, how effective it is. But we don't want to force the reader to read the whole paper, and so that should be here. The abstract should be more quantitative. This is a little too qualitative. We want the quantitative results. But in this case, we'll have to read the paper to find out how effective it was. And so that's not good, I think. And then in the intro, they talk about, introduction. DNA is the primary carrier of all genetic information. So it gives you a background, In this context, over the last 2 decades, the transition metal complexes have received considerable amount of attention in tools for pharmaceuticals. In particular, ordinary saturated, so they're telling us what's been done with this complex in DNA. And then, they interact with the DNA by non-covalent interaction. The non-covalent interactions is intermolecular forces such as electrostatic, minor groove, major groove, partial intercalative, and intercalative. Intercalative just means it slides in between the layers or grooves of the DNA. However, there's still uncertainty in the exact location of the binding mode. So this tells us the state of the art. There's still some uncertainty in the binding modes here. Further studies are necessary using different structural ligands. So this is a structural paper as well. It's factors talking about it. So we can get a good background of what's going on. It's been largely accepted that these probes for DNA structure determination, DNA photocleavage sites, DNA-mediated electron transfer. Recent reports, so they're telling us how this has been used in structural analysis of this. So this is a good introduction. This is a multi-paragraph introduction, which gives a good review of what's been done in the past. And then they have lots of references here, which you want to see, lots of references. So we can read the other papers if we want, to find out exactly what these people did, like J. Thomas and co-workers have reported the successful application of dinuclear complex, light switch complex, and this, whatever. All right, and then they're probably going to talk about what they're doing in this paper. As part of a project aimed at systematic structural alteration with a view to elucidate structure-activity relationships, here we report the synthesis. So now they give all the background, now they're telling us what they're doing here. How this fits in with the work that's been done. So what you'll do is you'll do a little bit of search, internet search, and see, what aspects of this. You could talk about things like sulfate, the significance. Why do we need to know how much sulfate is in there? What's sulfate used for? Do you know what sulfate's used for? So you learn a little bit about sulfate and why anybody would care how much sulfate's in the sample, that kind of stuff. Or you would maybe or you'd look at gravimetric analysis. So using gravimetric analysis. This paper is a little bit different than the format I'm going to show you back here. I put the paper. All right. We're not doing a theoretical, this is not a theoretical study here. What we're doing is experimental work. So the next section is experimental details or methods and materials. So in the experimental section, this is like the recipe, you know. This is the recipe, but it's beyond the recipe. The recipe's procedure. Recipe is supposed to tell you what you're supposed to do. Here, this is your observation. So what we do is we just kind of collapse our observation into one or two paragraphs. And the observations are just raw observations, like, you know, how much water, how much unknown, how many grams, you know. And so this is what you did. And the reason you do this is so that people can repeat the experiment exactly as you did it. So let's say you weighed out 0.2385 grams of unknown. Well, if they want to repeat it exactly like you did it, they'll weigh out 0.2385 grams of unknown and see if they get the same results, you know. Because in science, we make sure that we confirm and test people's hypotheses. Okay, in research reports, this section can also be called experimental methods, experimental section, or materials and methods. Check the specific publication. So whatever, I don't really care which one you use. For experimental work, give enough detail about your materials and methods so that other experienced workers could repeat your work and obtain comparable results. So if you want to repeat their work exactly as you did it, then you have to include enough details so that they can repeat it exactly like you did it, down to how many milliliters of water you added. When using a standard method, reference the appropriate literature and give only the details needed. So a standard method means, like, okay, you did vacuum filtration. And vacuum filtration is standard method, so you don't have to say, okay, I took a I took a beaker and I washed it and then I dried it with paper towel. You know, washing and drying a beaker is standard. You know, you don't have to give any details with that, right? And so there are certain things, certain details that we do need to include here, even for standard methods. Like, for example, drying. You know, we dried certain things. And different people have different methods of drying. And so we'll talk about that. Identify the materials you use and give information on the degree and criteria of purity. But do not reference standard laboratory reagents. Like if we grab some 6 molar sodium hydroxide, that's standard laboratory reagent, so we can just say, you know, or the hydrochloric acid. I forgot what molarity. Do you guys recall what molarity you used for the hydrochloric acid? Was it 6 molar? Yeah. Something like that. But when you buy reagents, let's say we used a reagent, when you buy it, you usually cite who you purchased it from, who the manufacturer of that particular reagent is. And so there we'll reference that. And when you buy reagents, you can buy different degrees of purity. So they have like pharmaceutical grade, they have food grade, they have reagent grade, they have analytical grade. And so usually analytical grade's at the highest. Analytical is at the highest purity. But there are different levels of purity that you can buy, and it depends on how much you want to spend. So for example, food grade, is food grade very high purity? No, it's not. What are the impurities? When I was looking at the impurities, I bought some food grade sorbic acid, and I was looking at the impurity. The impurities are like not to contain more than this many parts per million lead, you know. So there's certain allowable things. You think lead, why would you want lead in food grade sorbic acid? Well, I guess there is lead in food grade because it's analyzed there. And so they have different things, arsenic, other things that might surprise you. But fortunately, they just use very little sorbic acid in things. And so we need to know the grades of the reagents that we use. Describe your apparatus only if it is not standard. Well, some people just copied and pasted the vacuum filtration apparatus from the lab manual into their report. You could do that, you know, but we modified it a little bit, and so it's not exactly the same. So, for example, in the lab manual, they used a water aspirator for the vacuum. We didn't use a water aspirator because it wastes too much water. There's a little T thing. As the water flows through the T, it creates a little bit of vacuum. A huge waste of water. We used to use those, but not anymore. And so, yeah, if you do that, well, one, you have to make sure anything you take from the internet or take from a journal, you have to reference it. It has to be clear that you took it. So let's say you, like in the introduction, you'd like, oh, this is really nice sentence, and you use that. Well, make sure you put quotations around it and cite the source of that. You know, just don't copy and paste it because that's plagiarism. Or if you do, you got to make sure you change it enough so it's not plagiarized. So make sure you do that. Some people just do. Some people, I don't know, they just copy and paste it off the internet without citing it. That's very bad. So do that. So this section's actually really easy to write. This is like when I was doing papers, this is the easiest section to write because you already did it. You know, you have your observations there. This is essentially just writing out your observations in a more readable fashion. And so I always did this section first because it's so easy. Avoid using trademarks and brand names of equipment and reagents. I do brand names for reagents sometimes. Actually, all the time. We did Aldrich 99%, something like that. Describe the procedure you use unless they are established and standard. Note and emphasize any hazards such as explosive tendencies, toxicity. In a separate paragraph introduced by the word caution, include precautionary handling procedures and any other safety considerations. Some ACS journals and books will also indicate the hazard as a footnote. There weren't any significant hazards in this, just regular routine hazards, so I don't think we need to worry about that. Okay, this is for theoretical papers. In theoretical papers, you're approaching it differently. You know, you have the experimentalists and the theoreticians. So we're doing experimental paper here. You know, they publish in the same journals. Then we have results and discussion. We're going to keep these separate. A lot of papers combine results with the discussion, but we'll keep them separate because there's a difference. Do you know what the difference between results and discussion is?
Summarize everything.
I'm sorry?
Summarize everything.
The results are things like this. The results are would be like how many grams of unknown did you get? That would be a result. How many grams of unknown did you weigh out? Because that's just fact, factual knowledge, factual observations. How many grams of dried precipitate did you get? How many grams of dried white precipitate did you get? That would be factual. That would be results. However, if you said, I got this many grams of barium sulfate precipitate, that is not results. because you're making an assumption that that white precipitate that you collected in the Celis crucible is pure barium sulfate. How can you conclude that? Because a lot of people in science, skepticism is an important part of the scientific method. And so somebody's going to say, well, how do you know it's pure barium sulfate? Right? And so in the results section, we would never say we collected this many grams of barium sulfate. We would say we collected this many grams of white precipitate. And then you have to prove to the reader that that white precipitate is actually pure barium sulfate. Now, how are you going to prove that white precipitate is pure barium sulfate? And so the results are very short. Our results section is how many grams of unknown, and how many grams of white precipitate did we get, basically. And then we have this. The discussion section is where you're going to convince the reader that that is really barium sulfate. And not what? And not a mixture, or not something like, what else likes barium? Does anything else like barium ions? Any other anions? Phosphate. Phosphate's also a white precipitate. Hydroxide's a white precipitate, and chromate. But chromate is a yellow precipitate, but you could have small amounts of chromate in there and not really be able to detect it because it could be masked by the white precipitate. It could be a mixture of precipitates. So somebody might argue, I don't believe you. It could be phosphate, it could be carbonate. Those are white precipitates too. You got to prove it to me that it's pure barium sulfate. How are you going to prove it to me? And so the discussion is the longest part of the paper. The discussion's where you're going to go through and convince the reader that, yes, this method works. And it's not yielding interfering precipitates like barium carbonate, barium phosphate, barium hydroxide, and barium chromate.
Let's say hypothetically that you contaminated your sample and that you didn't.
If you contaminated your sample, then you gotta convince the reader that you didn't contaminate the sample. Of course, if you contaminated the sample, then nobody's going to publish this paper. You got to convince the reader that this is not contaminated, and etc. And so, how did you prevent contamination from occurring? Yeah, so there are certain things that we did. Obvious things like washing. What did you wash it with? Did you wash it with water, DI water, or did you wash it with dilute HCl? Was it warm HCl or cold HCl? Why warm HCl? You got to convince the reader why you use warm HCl, or why use HCl entirely? Why not just use DI water? And there's certain things you got to convince the reader because they'll want to know. And so usually you write a paper like this, or you make a poster presentation, and you would go present it at scientific conferences. And at scientific conferences, you're going to be asked a lot of questions. And why are you doing that? And you should have the answer already, or the answer should be in the paper. This should answer all the questions. So if they read it, maybe they'll have some minor questions. But if there are some glaring things like, oh, it's contaminated, then they're going to start grilling you. That's why it's contaminated. Not grilling, but grilling in a nice way, They'll start questioning you.
Do you have to use all our 3 trials?
Of course. Why 3 trials? I talked about this too. Why 3 trials? To minimize random error, but why 3? Why not 4? Why not 2? Why not 1?
To be accurate.
Because 3 is the biggest payoff for.
Yeah, that's the most worth. Like if you did 10 trials, you might maybe like 2% more accurate.
You're right. Exactly. So that's something we talk about in the discussion section too, especially since this is a Chem 1A level. At higher levels, people wouldn't talk about this. But we're going to talk about higher level because we're going to do one more thing for statistical analysis. And this is something we're going to do in the computer lab, or we could do by hand. We'll probably do it by hand, a calculation. But the discussion, this is what most people are really interested in, is your discussion section. Because this is where you're going to convince the reader that what you say is correct, that they should believe you. So anyway, but this is your analysis. This is your interpretation. And so what's happened before is the theory evolves. And so there are old papers there. There are old papers where they took the results because the results never change. Even with time, the results never change because the results are experimental fact. But as the theory evolves, then there are papers out there that are published with the title Reinterpretation of So-and-so's work. And so what they do is they throw away their discussion because they don't believe their discussion at all, and then they take their results and come up with a whole new analysis of their results. Does that make sense? And so this is why we try to keep them separate, results from discussion, because results will never change. However, the discussion, your analysis of those results might change as new things are being learned. We're going to do some statistical analysis for this experiment.
You say we need to know the grade of the chemicals that we were using?
Usually, that's written. I always put in the grade of the chemical we use. Most of the stuff I did was using reagent grade, which is the cheap stuff. See if we can find a synthesis paper.
Is that what we use for this one?
Yeah. Here's a paper on catalysis. In the introduction, they give us a little bit of... Actually, this is a review paper. And this is a review paper. This is here. Today, worldwide catalyst sales exceed 5.9 billion per year. And it has been estimated that catalysts generate fuels and chemicals worth 2.4 trillion annually. So this is kind of a review paper. Here. Mesostructured. This is a big topic at UCSB, mesostructured material. One of the catalysts that people are looking for are catalysts that convert like methanol into gasoline. There are certain catalysts that do this. But you can make methanol from methane. So you take methane, make methanol, and then from methanol convert it into gasoline. A lot of these papers have a paywall, unfortunately. So I could buy 48-hour access for 12 bucks. That's not too bad. Or PDF for $49. It's gone up. Price has gone up, like everything else. Let's see about there. This is unusual because what they did was they put the synthesis and the results and discussion. So they combined experimental results and discussion section all in one. So they don't talk about their starting reagents here. They did, earlier when I was saying, do you believe in atoms? Yeah, everybody believes in atoms nowadays because you can see atoms with X-rays. And so this is called X-ray diffraction, single crystal X-ray diffraction. And you can see how all the atoms are oriented and bonded. You can get the bond distances and other stuff from this type of analysis. So all these are what we call XRD structures. The only atom that's hard to see with X-rays is hydrogen. And so hydrogen, we don't. If you want to see the hydrogen, you do a different thing called neutron diffraction, where you shoot neutrons at the structure, and the neutrons will interact with the hydrogens, so you can pinpoint those as well. And so the hydrogens are determined in structures like this by calculations, theoretical calculations. And the reason is there's not very many electrons there. Okay, so I'm going to stop here now. I'll talk more about this Wednesday, okay, but I think that's enough for today. So start thinking about the paper. This is a paper you're going to co-author with your partners. So you can work on it together with your partners, or you can work on it alone. You could do single author or multiple authors. I'll leave it up to you how you want to work on this. Some people prefer to do it all themselves because usually when you work with partners, one person does all the work anyway. And so you might be of that type. But it's good to have co-authors, and it's good to work well with others. I'm sorry? We're going to have a rough draft of the paper due. So we're going to collect rough drafts. Or also, if you have any questions, coming up pretty soon. I'll give you a date. After I finish talking about this, we'll have a rough draft. All right, so start researching it, finish up the calculations if you haven't, and then I'm going to do some statistical stuff on Wednesday that we're going to look at. And so there are going to be some additional calculations you're going to do for this lab that you're going to include in your paper. Okay. All right, any questions on that? So for today, what we're going to do is on exam 2, you're going to have to predict products, for metathesis, acid-base, and redox reactions. And so we're going to get some more practice with those. And so what you're going to do is you're going to continue. If you did those metathesis at home, I can check them, and then start on the redox. So all the redox reactions that we did in the lab, I want you to write out all the equations for that, including the driving force. And then at the end, we're going to do some skeleton redox. On Wednesday, I'll talk about some more advanced skeleton redox reactions we're going to do. All right, so go ahead and just continue working on that, and I'm going to check them off. The equations, these checked off equations is what your report grade is going to be based on. It's going to be based on how many correct equations you generated.